Okay, before we dive into our studies of our sun, I just have a few review questions here for you to go over. So these concept questions, I'll just pause for the question and then I'll go over the answer. So go ahead and read the question, select your answer, and then unpause the video. So hopefully you answered lens for a refracting telescope. A reflecting telescope uses mirrors, but a refracting telescope uses lenses. How about this question? The main reason astronomers seek funds to build larger telescopes is to... So what is the main purpose of wanting larger and larger telescopes? Pause the video and answer. Okay, so it's all about wanting more light. So remember, the best way to think about telescopes is that it's one big light bucket. The more light, the better. So the bigger our bucket, the bigger our telescope, the more light we can collect from distant objects. How about this concept question? When light from the concave primary mirror of a telescope is reflected by a small secondary mirror through a hole in the primary mirror, it's called what? It really helps to draw these out. So think about drawing it out. Hopefully you answered Cassegrain telescope. Because a Cassegrain telescope has the image going down through the center hole of the telescope. Okay, how about another one? The dark absorption lines in the solar spectrum are caused by absorption of what? So pause and take a moment to answer. All right, they're caused by the absorption of sunlight in a cooler layer of gas overlying the hot solar surface. And we'll talk about that today in this lecture, that the atmosphere of our sun is what we call the chromosphere and the corona. Okay, so let's dive into the sun, chapter 16. So I just wanted to put up the temperature scales again because we're going to talk about temperature scales from here on out being in Kelvin. So when we discuss temperatures within the sun and then temperatures of other stars in chapter 17, we're going to be using the Kelvin scale. So I just put this scale on here to give you the three primary temperature scales we have are Celsius, Kelvin, and Fahrenheit. So you're probably the most familiar with Celsius and Kelvin. So Celsius is the most common throughout the world, although in the United States we're more familiar with Fahrenheit. Celsius is based on the temperature of water at sea level. So water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. Kelvin's scale, on the other hand, was named after the British physicist Lord Kelvin. And so absolute zero is the temperature at which atomic motion is at the absolute minimum. So those molecules stop jiggling, and nothing can be colder than 0 degrees Kelvin. So if you were just curious about how to convert between the three temperature scales, I put this little conversion chart on here for you. But nothing to know for this class, just for your own knowledge if you want to be able to convert between the different temperature scales. Okay, so our sun. Our sun, we typically say, has a temperature of 5,800 degrees Kelvin, or sometimes I round that and say about 6,000 degrees Kelvin. Well, that's really the temperature on the surface of the sun, okay? And the surface we call the photosphere. In the center of the sun, it's much hotter. That is where the thermonuclear reactions are taking place, the furnace, okay, where the sun is heating up. So that's at 1.5 times 10 to the 7 degrees Kelvin in the center. So the sun shines because it's generating energy by converting hydrogen into helium in the core, okay? And a byproduct of this is something called a neutrino we'll talk about. So our sun has a lot of mass, okay? It's about 1,000 times more massive than all the planets, moons, comets, asteroids, etc. combined. Its mass is about 2 times 10 to the 30 kilograms. And this mass is really made up of mainly hydrogen and helium. And our sun is what we call a main sequence star, which we'll cover more in chapter 7. So as we mentioned in the previous question, our sun does have an atmosphere. Okay, so we talk about the surface being the photosphere and this atmosphere around the sun. We also talk about our sun being active, and one of the ways we think about our sun being active is by the existence of sunspots, and we'll talk about those today as well. And finally, the luminosity of our sun. Luminosity can be measured in energy per second coming out of the sun. That's in the measurement of watts. So it's how much energy is pouring out of our sun every second. And we'll cover about luminosity a bit more in chapter 7 about properties of all stars. Okay, so how does the sun give off energy? So in order to understand how the sun gives off energy, we need to recall the basic ideas of the atom. So you need to understand how a single atom can produce energy. So recall the makeup of an atom. We have the nucleus made up of protons and neutrons, surrounded by a cloud of electrons. So the nucleus is where the action is happening. Okay, it's the interaction of atoms of hydrogen within the sun, particularly in the nucleus, the neutrons and the protons. So what's neat about this is actually showing that mass can be converted into energy. Going back to Einstein's famous equation of E equals mc squared, what he's saying in that equation is energy can come from mass, and that's what's happening in these thermonuclear reactions. So how could this happen? So think for a moment, how is mass in a form of energy? Okay, so how do we get energy from mass? I think that question is worded very poorly. I'm trying to think, how did I write that like that? But what I'm asking here is, how do we get energy from mass? Where is that energy from? So take a moment and think about it before going to the next slide. Okay, so we get energy from mass because there's a tremendous amount of energy stored within every atom. So the question is, where is that energy stored? It's stored in the nucleus. That energy is stored between the bonds of the protons and neutrons, and that's where the reactions are taking place, which then release energy when those nuclei interact with each other. So in our sun, the interaction of the nuclei is through fusion. Two atoms of hydrogen combine to form helium, and it's really going to be four protons of hydrogen forming to form one helium atom. So some of that mass that is converted in the process of fusion is converted directly to energy that radiates off out of the sun. And that energy is what we see and feel as sunlight. And this fusion reaction takes place deep in the interior at the center of the star, where it's hot enough for fusion to occur. Recall when we talked about the protosuns and protostars in the formation of our solar system, we discussed how the sun really didn't become a star until those thermonuclear reactions happened in the core. It got hot enough for those reactions to take place. So thermonuclear fusion is the fusing together of nuclei. So two hydrogen nuclei would be hydrogen fusion. And it takes place at very high temperatures. And part of the reason we can get such high temperatures is because of the high pressure in the center of the sun. So it's a combination of high pressure, which causes high heat. And so we get four hydrogen protons interacting, and I'll show you how this works, to come out to give us helium, a heavier element, and energy. And we call this the proton-proton chain. So let's look at how this works. So we have two protons of hydrogen floating around in the center of the sun. They interact through fusion, and one of the proton charges and changes into a neutron, okay, which we're representing from blue here. So the proton and the neutron form a hydrogen isotope, and in this reaction some energy is given off. We have one byproduct, which is a particle called a neutrino. It's a massless particle that we're able to detect. And in addition, we also have energy given off from this reaction, okay, in the form of gamma rays. Now we have this isotope of hydrogen floating around in a soup of all these protons. So this isotope of hydrogen combines with one of those protons again, and now we get an isotope of helium. This reaction also produces some energy in the form of gamma rays. Now finally, a whole bunch of these isotopes of heliums are floating around. Two of them interact together, okay? And so therefore the two protons and the two neutrons from these two helium nuclei rearrange themselves to form a complete helium isotope, with leaving over two extra hydrogen protons. So that's how we end up taking four hydrogen protons to create our helium, plus energy left over. So that's the basics of the proton-proton chain. Now these two positive protons from hydrogen go off floating back in that full soup of the center of the sun to be used again to form more thermonuclear reactions. So that's how hydrogen is being converted into helium in the center of our sun. So mass and energy are combined and are conserved, but the mass is lost and it's producing energy. So this begs the question, what is the most abundant gas in the universe? Hopefully your answer is hydrogen, because it's that hydrogen reaction that is so important to form all the heavier elements. So that means, what is the sun made out of? Well, the sun is made out of primarily hydrogen and helium gas, so that hydrogen is fusing into helium through thermonuclear reaction. So essentially you could think of the sun as one large ball of burning, if you want to think about it, gas. Okay, so it's just a ball of gas. So how does that ball of hydrogen gas keep its shape, right? It's a spherical shape. The sun is a sphere. Well, it keeps that shape by what's called hydrostatic equilibrium. So you can think of this simply as the balancing of forces. So in general, the sun doesn't undergo any kind of dramatic changes. Okay, it doesn't shrink a lot or grow very big over, small amounts of time. So it's all about pressure and balancing of forces. So the force of gravity pulling down on the gas is balanced out by the outward internal force pushing outward from the pressure of the reaction inside the sun. And that's hydrostatic equilibrium. So if we use the laws of physics, we can construct a theoretical model of the interior of the sun. And this is where we can construct our model of hydrostatic equilibrium. So a slab, if you imagine a slab of solar material, so I'm going to go to the next slide here. Okay, so here's a slab of solar material. It's in equilibrium, meaning it won't move up or down within the sun. So that means the pressure from below, okay, has to balance out the pressure from above. So the pressure above the slab, okay, the weight of the slab itself, okay, and all the layers above it are pushing down on this layer of gas, okay. Now, the pressure below, okay, is the thermonuclear reactions trying to push out of the sun. If those thermonuclear reactions cease, if they stop, all the pressure from above would win and the star would collapse. So it's in this nice hydrostatic equilibrium. So remember, when the protostar was forming, it was trying to shrink down and down and down because gravity was pulling harder and harder until those thermonuclear reactions took place. And then boom, they have the outward pressure and the star can keep its form. So one way to think about this is just how we think about pressure increasing within the ocean. So at the very center of the sun, the pressure is very high. So you increase pressure with depth. The same thing happens in the ocean. We have super high pressure at the bottom and lower pressure at the top. So the downward pressures of the layers above counteracting the upward pressure of the gases below. So an example of hydrostatic equilibrium in the real world would be scuba diving. When you scuba dive, you use your buoyancy device, okay, your vest, to add air into your system so that you can rise up against the downward force of gravity and the upward force of the pressures below. You add weight to your belt so you can sink further. Okay, you're playing with hydrostatic equilibrium when you're scuba diving. The same kind of thing is happening within the sun, just different slabs of material are going through this same dance of upward and downward pressure. So I'll pause here and we'll continue here in the next video.